Okay, so in this video we're going to start off by talking about motion with air resistance, which we've ignored before in the past, and then we're going to talk more about static and kinetic friction. Okay, so far this year when we've been talking about objects that have been falling, we've only been talking about objects that are in free fall. By definition, an object in free fall has only the force of gravity acting upon it. And I don't know if we've ever seen that particular definition of free fall before, but that is the definition of free fall. Again, that the only force acting is the force of gravity. But of course, in real life, there is air resistance, or there's a force that we call drag. Drag, I guess, is a more generalized form of air resistance because it doesn't have to necessarily be falling through air. If you imagine, let's say, dropping something into a swimming pool or a bowl full of honey or something like that, it's not going to be in free fall. It's actually going to fall kind of slowly as it works its way through that material. And so more generally speaking, we call this force a drag force, but in the context of air resistance, we'll call it air resistance. Either of those are fine, but drag is a more general term. So basically, here's how this works. Generally speaking, this drag force, this air resistance force, typically depends upon the velocity of the falling object. And what I mean by that is this force is not actually a constant force. It's actually one that changes as a function of time. And so here's how it works. When you drop an object, even if there is air resistance, as the object begins to fall, there's no drag force because the initial velocity of the falling object is 0. Okay, that means right when it begins to fall, it is in free fall. But as the object falls faster and faster, what happens is the drag force is actually going to increase. And kind of like how friction always opposes motion, the drag force is going to oppose motion as well. And so if you have an object falling down, the drag force would be going up. Now, at some point, the upward drag force is going to balance out the downward force of gravity, the downward weight, and when that happens, the object is going to fall at a constant velocity. And so, in other words, the object is no longer speeding up or slowing down, it's falling at a constant velocity. And the velocity at which this happens is called the terminal velocity. So an object falling at terminal velocity has a net force of 0. It has two forces on it, the upward drag force and the downward force of gravity. And because it's no longer falling any faster, the drag force is basically stuck at that one value. And so even though a lot of the time we do these problems with air resistance, this type of effect can occur when objects fall through any type of fluid, whether it's air or a type of liquid like water or oil or honey or something viscous like that. And so just to give you an idea of the concept behind this terminal velocity and this drag force, I'm going to link some videos in that I want you to watch. They're all pretty short, but hopefully after watching these 3 videos you have a better understanding of the concept that we're talking about here. Okay, so this diagram, we've actually seen this before because it was a past warm-up question, but this basically is a diagram showing you how an object falling under the effects of a drag force like air resistance, how its free body diagram might change over time. So you can see in diagram A, when the man jumps out from the helicopter, he is in free fall. Okay, by definition, the only force acting on him is the force of gravity. Because his initial velocity is 0, he's not moving right when he begins to fall, and so there is no drag force. Okay, there's no force from the air. In diagram B, you can see that he started to speed up a little bit as he's falling. Now he's no longer in free fall. There's an upward force from the air resistance acting upon him. Now in this case, the overall net force is still down, and so he's still accelerating down. His velocity in the downward direction is still increasing, and so he's still falling faster and faster and faster. But as he does that, you can see in diagram C, now the overall net force is still down, but it's not as much, okay, because now you have 700 newtons up and 833 newtons down, and even though those two forces aren't quite balanced out yet, the acceleration in diagram C is less than the acceleration in diagram B or A, because now the overall net force is less, which means the acceleration is also less. And then by the time you get to diagram D, you can see that he is actually falling at terminal velocity at this point. The upward force from the air is balanced out by his weight, his downward force of gravity, and so he's now falling at a constant velocity. And I think I've mentioned this in class before, but this concept of terminal velocity that you see the man falling in, that's one reason why, for example, if you were to drop a penny off the Empire State Building, if it hit somebody, it wouldn't cause enough damage to permanently injure them. Okay? And this is something that Mythbusters actually tested out if you want to look that up on YouTube. But that's basically the concept of falling with air resistance. And so the only problems that you would see on an IB exam related to air resistance are problems like this that we're going to see, where it's really focused on what's happening at one moment in time in the problem. Because the force of air resistance actually changes over time, those problems can get kind of mathematically complicated, and they actually require calculus to do a full analysis. And so typically you'd only be asked to deal with the problem at one single moment in time. Okay, so let's do some examples with this before we get to friction. Okay, so a simple example looks like this. We have a 4-kilogram box, and it's thrown out of an airplane. And it says after the box falls for a few seconds, it reaches a terminal velocity of 45 meters per second. Okay, now if you don't know what terminal velocity is, then that doesn't help you answer the question. Remember, that is the velocity at which the object is basically no longer accelerating because there's a net force of 0 on the box. So the FBD, right when it leaves the plane, would look something like this. The object would be in free fall, only the force of gravity going down. After the box has reached its terminal velocity, remember it's still falling down, but now that downward force of gravity is balanced out by the upward force from the air, that drag force acting upward. Okay, so that's what those two free body diagrams would look like. Now the third question says calculate the net force on the box when it's falling at terminal velocity. Now if you've been paying attention, of course, you know the answer has to be 0, because if the object is not accelerating, its net force is 0. But if you want to write out the sum of the forces, what you would basically do is you would do a Newton's second law equation where you have F net y equals may, and at some point ay is going to reach 0 because it's no longer going to accelerate, but the sum of the forces would still be the same. Okay, and so if you had to, you could calculate the upward drag force, the upward force from the air resistance, knowing that it balances out the force of gravity. So here, if you actually wanted to calculate what the force up was, you would just say, Fg equals mg. We would do 4 times negative 10. Get the force of gravity is negative 40 newtons. And then you could say F air plus negative 40 equals 0. And so F air would be 40 newtons. And that's not asked of you in this question, but that's how you would solve that type of problem if you were asked about the force of air resistance at terminal velocity. Okay, so pause there if you need to look at that some more. Okay, and then just to show you one more quick example, this is actually from an IB exam a couple of years ago. And so I want you to look at this question and see if you can answer this question on your own. The question says, a raindrop falling from rest at time t equals 0 reaches terminal velocity. Which graph best represents how the speed v varies with time t? And so this actually has to do with motion graphs, and it's asking you which of these velocity time graphs would fit the motion of a raindrop falling with air resistance. And you know there's air resistance because it says it's talking about terminal velocity. Okay, so see if you can answer that question on your own. Okay, so hopefully you figured out that the answer to this question is B. The key concept here, well, there's a couple of key concepts. Number one, with terminal velocity, what's basically happening is the object is going to fall faster and faster and faster, but at some point it's going to reach a set speed and it's not going to fall any faster. And so you're looking for a velocity time graph that basically levels off, and the only one that really does that is B. Now, the other way you could think of this question is, on a velocity time graph, the slope of the graph represents the acceleration. So you can see here the slope starts off pretty constant, but as the graph goes on, it gets less and less and less and less and less steep and eventually just becomes horizontal. Okay, so by the end, it has no slope. The slope is 0, meaning that the acceleration is 0, meaning that it's reached terminal velocity. Okay, and so that's one of those concept questions where as long as you understand just some very basic things about terminal velocity, that was a pretty easy question to answer. Or it should have been a pretty easy question to answer. So pause there if you need to look at that some more. Alrighty, so I'm going to stop this video here, and then I will do one more video about friction, which is definitely the more important of these two videos because we're going to do a lot of problems with friction over the next couple units. Okay, so as always, please let me know if you have any questions, and I'll see you guys in the next video.